What happens if you drop a glass of water? Yes, it breaks because glass is breakable. What about a steel glass? Does it break when it is dropped? Steel is a metal and so it won't break. This is one of the properties of metals. Metals cannot be broken, but their shape can be changed. If heat or pressure is applied, metals can be drawn into wires, flattened into sheets, and molded into different shapes. Metals are malleable. Malleability refers to the property of a metal that allows it to be beaten into sheets. Ductility refers to the property of a metal that allows it to be stretched or drawn out into wires. Now, let's do a small activity. Here are some metals and non-metals. Select a material to see what happens when it is hit with a hammer. Select a material to see what happens when it is pulled through the wire drawing plate using a pair of pliers. From the two experiments that were conducted, can you tell which of these materials are metals? Click the metals to select them. Well done! Aluminium. You just saw how a metal can be deformed because of its inherent properties. Let's see how properties of malleability and ductility are used to create different objects. Different metals have different degrees of malleability and ductility. For example, gold and silver are ductile and malleable, but lead is only malleable. Which is the most malleable metal? Which is the most ductile metal? What are the other properties of metals?
Metals and non-metals. Metals such as iron, copper, and gold have distinct traits that help us to distinguish them from non-metals such as carbon, sulfur, and oxygen. At room temperature, almost all metals can be found in a solid form. Two exceptions to this are mercury and gallium. They are liquids at room temperature. Non-metals can appear in a variety of forms at room temperature. They may be solid, such as sulfur, a liquid, such as bromine, or gaseous forms. Metals will usually have a shiny appearance with a surface that reflects light. This property is known as luster. Non-metals such as carbon may be reflective, but they generally do not have luster. Metals are malleable, meaning they can be hammered and even pressed into thin sheets known as foils. Non-metals are less malleable and are more brittle. Metals are ductile, meaning they can be drawn into wires. Non-metals are not ductile. Most metals are hard. Exceptions include sodium and potassium, which are soft and can be cut with a knife. All metals are good conductors of heat and electricity. Non-metals usually don't conduct electricity very well. Metals are usually heavy and have a higher density than non-metals, causing them to sink in water. Solid nonmetals such as carbon are, relatively speaking, lighter and have a low density. Summary: most metals are solid at room temperature. Metals are lustrous, malleable, and good conductors of heat and electricity. Non-metals can exist in solid, liquid, or gaseous forms. Non-metals are poor conductors of heat and electricity.
Metals and non-metals can be differentiated on account of their physical and chemical properties. Let's test one of these chemical properties, namely their reaction with water. Metals vary in their reactivities and exhibit different reactions with water. Some metals like sodium and potassium have dramatic reactions with water. When sodium metal is gently dropped in cold water using a pair of tongs, it reacts vigorously, skittering over the surface of the water. Bubbles of hydrogen gas are liberated while sodium hydroxide solution is formed in the beaker. Cover the beaker after adding sodium. This will prevent it from exploding out of the beaker and cause damage. Also, avoid adding large pieces of sodium to the water, as it will result in a larger explosion. On the other hand, metals like iron react very mildly with water. Iron reacts with atmospheric oxygen and moisture to form a coating of its oxide. This oxide is commonly known as rust. However, the reaction is very slow, and it takes years, if not months, for iron to rust completely. Unlike some other metals, gold doesn't react with water at all. That's why it doesn't lose its luster for years. What about non-metals? Do they also react with water? Non-metals usually do not react with water. When you drop a piece of carbon or sulfur in water, no reaction occurs. In fact, phosphorus, which is highly reactive, is stored in water to prevent its vigorous reaction with atmospheric oxygen.
Generally, in a displacement reaction, an element reacts with a compound. This element is more reactive than one of the elements in the compound. So, it displaces this less reactive element to form a new compound. Different metals have different degrees of reactivity. The reactivity series of metals acts as a tool to predict how these elements would react and what products would be formed in some chemical reactions. Let's try a small example to prove this. What happens when we place an iron nail in a copper sulfate solution? It is quite amazing to see the color of the solution changing from blue to green and a shiny thin film of copper deposited on the nail. If we look at the reactivity series, we see that iron is more reactive than copper. Hence, it displaces the copper from the copper sulfate solution. Let's check your understanding with a small interactivity. Can you guess which metals would carry the displacement reaction in the following examples? Click the metal that displaces copper from copper sulfate solution. Excellent. Magnesium, being more reactive, displaces the copper. Copper, being more reactive, displaces silver. Zinc, being more reactive, displaces copper easily. Let's summarize what we have learned about displacement reactions. Have you ever wondered why silver items look dull when exposed to air over a period of time? Have you noticed that aluminium vessels also gradually lose their bright metallic luster? Metals like silver and aluminium react with oxygen to form metal oxides. Have you ever seen red-hot burning coal? When you burn carbon, a non-metal, in the presence of atmospheric oxygen, it releases a gaseous, non-metallic oxide. Reactivity of different metals differs, and so do their reactions with oxygen. Click the metal to view its reaction with oxygen. Sodium is a highly reactive metal. However, its reaction with oxygen at room temperature is rather slow. Sodium, when heated, burns with a bright yellowish-orange flame. Insert the burning sodium in a gas jar containing oxygen for a while. Sodium burns more brightly, releasing a lot of heat, leaving behind a white hygroscopic powder of sodium oxide. When magnesium is ignited and placed in a gas jar containing oxygen, it burns rapidly, showering brilliant white sparks and releasing a lot of heat. The white ash that settles down is magnesium oxide. Magnesium burns with an intense flame, so avoid looking directly at the flame or wear safety goggles to cut off the ultraviolet light. Copper usually does not burn in oxygen. However, when it is heated, it gives out a blue-green flame. When the copper is transferred to a gas jar containing oxygen, it gets coated with a black powder. This black coating is cupric oxide. Like metals, the reactivities of non-metals also vary. Click the non-metal to view its reaction with oxygen. The combustion of carbon and oxygen is a slow reaction. Generally, carbon doesn't burn by itself. However, when heated on a burner, it starts to glow slightly. If we introduce it in a jar containing pure oxygen, it would glow red hot, producing colorless carbon dioxide gas. Sulfur is a yellowish soft solid. When you heat it in a deflagrating spoon, it starts melting and becomes ruby red in color. Burning sulfur, when introduced in an oxygen jar, gives an intense blue flame. It also produces colorless sulfur dioxide gas, which has a suffocating odor. Use only a small amount of sulfur powder to carry out this experiment. The sulfur dioxide gas formed during this reaction is highly toxic and can lead to asthma attacks. When red phosphorus is heated in a deflagrating spoon and added to the oxygen gas jar, it instantly reacts with atmospheric oxygen and produces white fumes. These white vapors eventually fall down like flakes of snow and form a highly hygroscopic powder of phosphorus pentoxide. Be careful while handling red phosphorus as it forms toxic fumes when in contact with air. We have observed some of the spectacular reactions of metals and non-metals with oxygen. One more thing we need to test is the nature of their respective oxides. We have aqueous solutions of a metallic and non-metallic oxide. Let's test them with blue and red litmus paper. For metallic oxides, we find that a red litmus paper turns blue, whereas a blue litmus doesn't change color. This indicates that metallic oxides are basic in nature. Can you guess how the non-metallic oxide would fare in the litmus paper test? Red litmus remains unchanged while the blue litmus paper turns red in color. Therefore, it signifies that non-metallic oxides are acidic in nature. Let's summarize what we have learned so far.
In 1986, a road tanker in the UK exploded. Later, investigators found out that the solution of sodium hydroxide and water that the tanker carried reacted with its aluminium walls and produced hydrogen gas. The pressurized hydrogen gas finally burst out of the tanker, causing the explosion. That's why it's important to know how acids and bases affect substances. Click on each of the buttons to learn how acids and bases react with metals and non-metals. Most metals react with acids. In contrast, most non-metals do not react with acids. Let's see how different acids react with magnesium, copper and carbon. Magnesium reacts with dilute hydrochloric acid to form a salt, magnesium chloride, while liberating hydrogen gas. The instant reaction proves how reactive magnesium is. When a burning splinter is brought close to the flask, it explodes with a pop, confirming the presence of hydrogen gas. Copper doesn't react with hydrochloric acid. Carbon doesn't react with hydrochloric acid. In fact, non-metals typically do not react with acids. That's because to react with the acid, they need to lose electrons and displace hydrogen. But non-metals prefer to gain electrons rather than losing them. This experiment must be strictly carried under the guidance of an experienced person. Moreover, concentrated sulfuric acid can cause severe chemical burns. When magnesium is added to sulfuric acid, a salt, magnesium sulfate, is formed and hydrogen gas is released. Popping sound of the burning splinter confirms the presence of hydrogen gas. Copper doesn't react with dilute sulfuric acid. However, with hot and concentrated sulfuric acid, it forms copper sulfate and water, liberating sulfur dioxide gas. Carbon reacts with hot and concentrated sulfuric acid to form sulfur dioxide and carbon dioxide. Typically, non-metals do not react with dilute sulfuric acid. However, certain non-metals such as carbon react when heated with concentrated sulfuric acid. Magnesium reacts with dilute nitric acid to form the salt magnesium nitrate and release hydrogen. The popping sound of the burning splinter confirms the presence of hydrogen gas. Copper doesn't react with dilute nitric acid. Carbon, just like all non-metals, doesn't react with dilute acids. When magnesium is added to moderately concentrated nitric acid, it forms the salt magnesium nitrate. But instead of hydrogen, nitric oxide gas is produced. Copper reacts with moderately concentrated nitric acid to form copper nitrate and nitric oxide. As the nitric oxide gas moves out of the flask, it reacts with the oxygen in the air and forms nitrogen dioxide. Carbon doesn't react with moderately concentrated nitric acid. This experiment must be strictly carried under the guidance of an experienced person. When magnesium is added to concentrated nitric acid, a salt magnesium nitrate is formed. During this reaction, nitrogen dioxide is released. Copper reacts spectacularly with concentrated nitric acid. The moment it's added to the acid, copper reacts rapidly, releasing brown fumes of nitrogen dioxide. The liquid in the flask turns sky blue with the formation of copper nitrate solution. Carbon reacts with concentrated nitric acid to release carbon dioxide and nitrogen dioxide. Typically, non-metals do not react with acids. However, certain non-metals, such as carbon, react when added to concentrated nitric acid. Barring a few reactive metals, most metals do not react with bases. Non-metals react with bases. However, these reactions differ from each other and are quite complex. Click to view its reaction with sodium hydroxide, a base. Aluminium reacts with a solution of sodium hydroxide and water to form a salt, sodium aluminate, and liberate hydrogen gas. Copper does not react with the solution of sodium hydroxide and water. The reaction between a nonmetal, such as chlorine, and a base like sodium hydroxide is complex. Unlike the reactions between metals and acids, non-metal base reactions cannot be generalized. They are different for different substances and in different conditions. Let's recap the different reactions that acids and bases have with metals and nonmetals.
Reaction between metals and water. Metals such as iron, copper, and gold have distinct traits that help us to distinguish them from non-metals such as carbon, sulfur, and oxygen. But looking only at their physical properties doesn't tell us all we need to know. To better understand how metals differ from non-metals, we need to look at their distinct chemical properties. In this session, we'll take a look at one such property, how some metals react with water. If a metal reacts with water, it will form a metal hydroxide or metal oxide and hydrogen gas. Let's see how calcium, an alkaline earth metal, reacts with water. When we place a piece of calcium inside a beaker containing distilled water, we'll see bubbles begin to form immediately. These bubbles are from the release of hydrogen gas. The metal will soon turn into a white precipitate of calcium hydroxide, forming a milky liquid. If we wanted to write this chemical reaction as an equation, it would look like this. Solid calcium plus water will yield aqueous calcium hydroxide and hydrogen gas. Another metal, magnesium, will not react as vigorously as calcium. Let's watch how it reacts. Drop a magnesium strip into a test tube that also contains distilled water. At this point, we won't see any kind of reaction. But let's heat the test tube over a burner so that the water begins to boil. As it boils, magnesium will slowly begin to react, producing hydrogen gas and a magnesium hydroxide solution. The reaction can be represented as an equation. Solid magnesium plus water in the form of steam will produce aqueous magnesium hydroxide and hydrogen gas. Metals such as aluminium and zinc will also react slowly with cold water. But with steam, they will react quickly to form their respective metal oxides. However, even at high temperatures, metals such as silver and gold will not react with water. Summary. If a metal reacts with water, it will produce metal hydroxide and hydrogen gas.
Reaction between metals and oxygen. Metals such as iron, copper, and gold have distinct traits that help us to distinguish them from non-metals such as carbon, sulfur, and oxygen. But looking only at the physical properties doesn't tell us all we need to know. To better understand how metals differ from non-metals, we need to look at their distinct chemical properties. In this session, we will take a look at one such property, how some metals react with oxygen. If a metal reacts with oxygen, a metal oxide is produced. If we were to sum up this reaction with a general equation, it would look like this. A metal plus oxygen will yield metal oxides. Let's watch how this occurs by looking at how magnesium reacts with oxygen. If we touch a magnesium strip to a flame, it will burn brilliant white. Once it has finished burning, the remains will be a white ash, magnesium oxide. Let's try the same thing using a copper strip. When we heat a copper strip over the flame, it won't burn like magnesium did. Instead, we will see a black powdery layer of copper oxide forming on the surface of the metal. This tells us that copper is less reactive with oxygen than magnesium. If we heat gold or silver metals, no oxide will form on the surface. meaning they do not react with oxygen. Summary. If a metal reacts with oxygen, it will produce metal oxides.
Metals have been an integral part of our daily life since early ages. Metals are widely used in various fields. Automobiles, aeroplanes, bridges, cans, utensils, water boilers, all are made up of metals. Non-metals also have an important place in our daily life. Non-metals are used in making fertilizers, firecrackers, and as water purifiers, etc. The oxygen that we breathe in and the carbon dioxide that we breathe out are also non-metals. Let's explore the uses of various metals and non-metals. Click any metal to discover its uses. Aluminium has wide uses. Aluminium being malleable and a good conductor of heat, it is used in making utensils. Similarly, aluminium being ductile can be drawn into wires. Aluminium is also a good conductor of electricity. Hence, it is used in electric cables. We all are familiar with aluminium foil. It is light in weight and also lustrous. Aluminium foils are used in packaging of food items. Aluminium is also used in packaging of medicines. Aluminium in its powdered form is used in paints due to its anti-corrosive property. Copper is a good conductor of heat and electricity, due to which it is widely used in calorimeters and in making electrical wires. Magnesium is used for making fireworks because it burns with a dazzling light. Zinc is used in galvanization of iron and steel. Zinc reacts with oxygen to form a protective coat of zinc oxide, ZnO, which prevents corrosion. Iron is also an important metal. Iron is used for making mechanical instruments, buckets, drain pipes, trunks, etc. Iron is also used for making manhole covers, sanitary fittings, and immovable parts of the machinery. Steel, which is an alloy of iron, is used for making bridges, ships, and stainless steel is used for making utensils and surgical instruments. Gold is a precious metal. Gold is popularly used in making jewelry. Gold is also used in dentistry for fillings and other orthodontic purposes. Click any non-metal to discover its uses. We inhale oxygen during breathing. Oxygen is essential for respiration in both plants and animals. Oxygen is also necessary for combustion of fuels. Hydrogen is found in gaseous state. It is a colorless, odorless, and tasteless gas. Hydrogen mixed with equal amount of helium gas is used in weather observation balloons. Chlorine is widely used in bleaching. It is also used in water purification to kill harmful microbes. Nitrogen is widely used in making fertilizers. Nitrogen gas is used as a food preservative. Carbon is used in making pencil leads, as a lubricant in machinery, and as an electrode of electrolytic cells in its graphite form. Iodine is used in making iodized salt, an essential component of our diet. Tincture of iodine, that is, solution of iodine in alcohol, is used for dressing wounds. The correct answers are displayed for you. Let's have a quick recap of what we have learned.
What is the importance of purity of gold? You might have worn gold jewelry during functions or seen someone wearing it. They look bright and shiny and seem strong, don't they? However, these gold ornaments are not made of pure gold. Do you know why? Usually, the goldsmiths add specific amount of copper or silver to pure gold. So, why is this required? Let's discuss it in detail. Gold is a noble metal and occurs in nature in elemental form. Noble metal means that it can resist chemical action. So, it doesn't corrode and cannot be easily attacked by acids. However, pure gold is very soft. It is easily malleable or ductile. That is, it can be easily made into thin sheets or threads. Due to this, ornaments made using pure gold may bend or break if pressure is applied. This is why pure gold is mixed with specific amounts of copper and silver. A certain standard is used to measure the purity of gold. The purity of gold is expressed in carat unit. 100% pure gold is 24 carat. This purity measure changes as the percentage of pure gold varies. The most common measure of purity of gold used to make ornaments is 22 karat gold. It has 91.66% of pure gold. Here is a table which shows the percentage of pure gold present in different carats of gold. Based on the purity of gold or the carat value, the price of ornament varies. More the carat value, higher the price. Now, let's summarize what we have learned so far.